Hello, and okay, my slides are already up, thank you. So today we will talk about artificial intelligence or a neural network composing music for us. And I would like to think you about composition in terms of dialogue. So imagine talking to a machine. Well, that would be nice, right? So you actually probably have already done that by talking to an intelligent agent like Alexa from Amazon Echo or Siri from Apple, Google Assistant, Alice from Yandex, or Cortana from Microsoft. So who of you has actually in the past year talked to an intelligent agent? Please raise your hands. And who of you has enjoyed the conversation? Okay, quite some people have enjoyed it. So imagine now that you could talk to an intelligent agent, but using music as a language of communication. How that would work? Well, when we are having communication, we are usually having it simultaneously, but that's not the way that we use communication in music. So musical language of dialogue, I would say, is counterpoint. Counterpoint is a technique used for writing music with several independent melodies, and each melody is called a voice because originally counterpoint was vocal music, so music written for performance by a vocalist. And the melody is homophonic, meaning there is one pitch at a time. No simultaneously sounding pitches. And this technique, counterpoint, was mostly popular in European music in Renaissance and Baroque period, so somewhere between 14th and 17th centuries. The system that I will be talking about that implements counterpoint dialogue with computers was implemented in these papers. So imagine that you listen to a conversation simultaneously. That would not sound nice, right? So here is an example of two people speaking on top of each other. Try listening to them and focusing on what they say. So here I'm going to play you an example.
Imagine that somebody knocks on your door and offers to buy your house for more than you thought.
Could you make out what they were saying? Well, maybe if you focus on one of them, then you can. But it's not going to be like that in music. So in music, your brain actually has an amazing ability on focusing on several melodical lines simultaneously. And I'm going to give you an example from Mozart's Requiem, the part written for the solo performers. And they will be introducing melodic lines or melodies or their parts in a musical dialogue one by one. And you can try and focus on one of the lines, then focus on two lines simultaneously, then on three lines simultaneously, and finally try simultaneously following four melodic lines at once. Could anyone follow four melodic lines at once? Three melodic lines? Yes, okay. So there usually are up to 5 melodic lines in counterpoint. And that's not just because it's very difficult to follow them, but also because it's really difficult to compose them. Because there are a lot of rules in counterpoint that one has to follow for it to sound nice and counterpoint-like. And The rules are very strictly defined in species counterpoint, which goes from first to fifth species counterpoint or free counterpoint. And the rules are usually concerned with well separating the voices, so you could actually follow them separately. And the separation comes from preferring contrary motion and not parallel motion, because when you have several melodic lines moving simultaneously in one direction, your brain tends to group them together and you cannot separate them well anymore. Then you try to especially avoid parallel fifths and octaves because of the overtone nature of harmonic instruments, where the major overtones fall exactly on the octave and on the quint, on the fifth note from the fundamental frequency. So your brain is especially apt to group them together if they are in these intervals. And usually between 2 and 5 voices, because more it will be really difficult to both compose and listen to. And in this talk we will compose, our AI will compose 2-part counterpoint for us. Computer music generation has a really long history, and in the past 20 years it's mostly neural network based. And recent successes were related to recurrent neural networks, then WaveNet, and the most recent newcomer that shaked up all of the natural language processing and music composition, transformers. So the reason why transformers became so popular are because they can learn from a much larger context and keep in mind a much larger context than RNNs, LSTMs can, because of the vanishing gradient problems. So let's listen to the example of music composed by performance RNN and try to pay attention to the structure in this music. What happens here? We give to an RNN model, token by token, a pitch, duration, and velocity of a note. Velocity is how fast it is performed. This is why it's called performance RNN. It means that we also have performative qualities to it, so loudness and articulation. But it really lacks some, structure to it. It does sound nice, and in local parts of it, it looks like real music. But when you listen to 3 minutes of it, you'll get a headache. Now let's listen to what WaveNet can do. WaveNet is not given input token by token, but it's getting input on a digital signal sample level. From the usual 44,000 samples per second, it's downsampled to 4,000 samples per second. You cannot really go, or maybe they were, about 8,000 samples, but you cannot really go much less than that. Otherwise, it will, not sound nice anymore. So WaveNet comes. You can notice that it's much more interesting timbrally because it is generating on sample level and not on a token level where it's rendered. So it's not actually synthesized from symbolic music. It's actual performance by a computer where every digital signal sample is generated one by one. And now we come to the newcomer, the transformer model. mainly showed us the GPT-3 architecture. This is the predecessor, the GPT-2, a 72-layer neural network with 24 attention heads and trained on symbolic music. So it's more like performance RNN in the sense of input. And this is what it sounds like. So there was actually a melody and accompaniment, and you can separate everything and you can follow. And the MuseNet output you can actually listen to and enjoy for a longer period in time that you can bear listening to performance RNN or the predecessors as such. So what does Transformer do for us? It encodes the input using self-attention mechanism, which for each word of a sentence pays attention to the context around that word and using usually multiple attention heads encodes the input in such a way that it always knows which word each word refers to in a sentence. So here, for instance, je suis étudiant. These words are all connected. You need to put the verb in the right conjugation and so on. And with music, it's exactly the same. Music is actually a lot like language grammar. So you have stable tones in a musical scale. You have unstable tones. You need to relate them to each other, and you need to know where you are in terms of musical beat. So attention is a very relevant thing for music. So here, for instance, we give as an input a source phrase from the first invention by Bach. Da, 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 da. And then we expect it to be encoded. And for the transformer to make sense of the durations of the notes, the positions in the scale, and then to understand what it needs to respond. And the simultaneous response would be something like da 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 dum. So. And to train the counterpoint composer, we of course need a counterpoint music archive or a corpus suitable for counterpoint. And this is what we have in MCMA, Multi-Track Contrapuntal Music Archive, which was cleaned for every part to be monophonic and removing embellishments added by the performance and timing inaccuracies, which are usually introduced because lots of these MIDIs are created from a MIDI keyboard, so input by a human performer. And here is what we have in this archive. You can see that the music is quite old. And let's go through a very simple example of what happens when we feed in a famous Estonian tune into this system. So look at this music and try to recognize what it is. Well, it's a famous children's song. And we encode it in two different ways. One is just the pitch and the duration. So it's a text. And the other one, we encode it by adding relative positional encoding. There is a way to add relative positional encoding inside the model, but we can also add it inside within the encoding using a beat token. And it actually helps for the model to orient within the text. So it's an addition to self-attention with music, because for music it is really important to remember where you are at each token, because usually the stronger metrical positions have stronger tonal positions as well. And we have a much smaller model than the one trained by GPT-2 or 3, 6 layers and 8 attention heads. and we train our attention, key query and value matrices in the usual way for transformers. And here is what the model answers to our children's song. Well, it was trained on Baroque music. Let's see what it will do with Baroque music. The oboe part is composed by a human, and the piano part is composed by our model. Another example of Baroque music. Yeah, that was not the example. So it was evaluated with 4 different metrics in replacement of usual Turing test that is usually used for models like this, for creative models. There are different other ways of evaluation. And one of them could be human edit rate. So we let an AI compose, and then a human can correct the errors to their liking, and then we see how many mistakes the AI made. So here is an example corrected by a human. And for those of you who are not dealing with music composition, let's think about other possibilities that transformers can provide for us. So in business, transformers can not only be used for machine translation, which you've already seen, but also for text generation, the same way as sequential models can be used. Well, we've seen an example by Melis. They can be used for text summarization, or sentiment analysis. They can be used to create chatbots, and a very recent example from August, code generation. So we've seen a GPT-3 model trained to generate code by being given natural language input, description of the program, and then generating the code. So transformers are a really exciting chapter in machine learning currently, and I'm pretty confident that in almost every business they can be employed in some way. Thank you.